Well, thank you. Well, you know the basic story, right, of what I'm going to talk about, which is to write the software for a fairly complex machine. It's basically a computer with very strange peripherals that has to do something that has never been done before. So the something that it has to do, the part that has been done before, but not with quite this complex of a machine, is to go from Earth to Mars. It takes about 8 to 9 months. And if you think about it, that already is rather complex, right? You have a rotating body, the Earth. It's just spinning in space, rotating around the sun. And there's this other body that's also rotating and spinning at some predictable rate with respect to one another. But then you have to launch something when the moment is right, when the two planets are close together, and get it to the other planet. Now, it turns out that you actually have to go all the way around the sun. So basically, to compute the trajectory, you basically compute it so that the gravitation of the sun is dominant, and you fall around the sun. And if you're lucky, and if you plan it right, you hit just the right spot on Mars. Distance of about 350 million miles that you have to travel. And the target is a relatively small area on Mars. It's Gale Crater, which has a very high mountain. And the area that you're targeting is about the size of Hollywood. Now, we landed in almost the center of the ellipse. They calculated an ellipse. In this case, it was a much smaller ellipse than ever been used for any landing on Mars. There are currently 7 spacecraft on Mars, so we have done this before. All of those were landed by JPL, by the way. Lots of others have tried and failed. We've been lucky. We've lost a few as well, but 7 of them are on the surface of Mars, and 2 of them are still operating, including this one. So the reason for going to Gale Crater, there's this nice mountain here, but there is suspected to be, and now confirmed, an ancient riverbed. So you have this fan of a river flowing out, and there's very interesting stuff that you can do to determine if life could have existed once on Mars. So the landing site is about 12 by 4 miles, and we were about 1 mile from the center of the landing ellipse. So spectacularly well executed. So now, just to remind you, you probably have seen this. I've shortened this to about 1 minute. What happened on August 5th this year with the landing. So this is the animation, but then
we should have parachute deploy around
interspersed with the actual control room at that moment. Largest parachute ever used for a landing on Mars.
We are decelerating. Heat shield has separated. We're found the ground. We're down to 90 meters per second at an altitude of 6.5
So you saw the heat shields fall away as the back shell. The rover is inside the back shell.
Back shell separation.
Drops out of the back shell, has its own thrusters.
We are in powered flight.
None of this ever tried before.
We're at an altitude of 1 kilometer.
And of course, none of this can really be tested in the Earth's gravity.
Sky crane is started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars.
So when we got the confirmation that the rover had successfully landed, a lot of people, of course, were very relieved and surprised. But actually, this whole thing had happened 14 minutes earlier on Mars, but then it's the one-way light time of the signal. So this is one of the pictures taken from the rover itself, and you see the blast holes next to it, where the thrusters in the descent engine, when it lowered the rover on this tether down to the surface, you see that it blasted away the rocks, and that there's rock material on top of the rover itself. So that's from the descent engines. Of course, there are lots of things you have to worry about, and that people worry about a lot. Like you cut the bridle at some point, and the descent stage has to fly away. Has to really fly away a safe distance and not just drop down on top of the rover. There are lots of scenarios that they're going through in simulations to figure out what might happen and how you prevent the bad things from happening. Just one reminder how big this thing is. The thing was, the entire rover and the controls, etc., were built at JPL. All the software was written at JPL. The instruments came from external vendors, and they were assembled to the rover. But the thing was big, right? It's the largest thing ever flown to Mars. So that's the back shell. That's the thing where the rover was mounted into. So it nicely fits the size of a small car. On Mars, the rover weighs about 330 kilograms. On Earth, it's about twice that. Lots of things that can be said, but the question is, how do you make sure that it all works? Lots of testing, of course. Here's the rover when it was at JPL in a vacuum chamber. There are lots of tests that are being done. It's exposed to the same environment that is predicted to exist on Mars, and on the way to Mars, the vacuum of space, the sun, of course, heats up the spacecraft quite a bit, and if you're not careful, it heats it up on one side, and then it's very cold on the other side. So typically, you spin the spacecraft, in part for the thermal environment, but also in part for stabilization, that you can actually point to the right place on Mars. Lots of these kinds of testing that I'm not going to talk about, even though lots of people, hundreds, if not thousands of people are involved in this phase of testing. We're, of course, more interested in the software, and in the flight software team, we've often joked that we would do this mission without the hardware if we could. But of course, you can't quite get to Mars that way. So here's just a snapshot of all the phases of the verification and validation that goes into a system like this. Of course, you want to make sure that things will work on Mars, but it's very hard to do experiments on Mars. It's kind of costly, and it's kind of embarrassing if the experiments don't work out. So we do a lot. We do everything on Earth here. So there are two types of tests that are being done. One is the flight system stress testing, and one is the flight dynamics testing. So it's basically making sure that you can actually get to the planet and not miss it by a huge amount, which has happened in the past. So there are these different types of test beds. So there's lots of hardware that is being built and software that is being built to allow us to test different parts of the rover and its software in as faithful as of an environment as possible. So there's the guidance and navigation software and the EDL software. EDL software is the entry, descent, and landing software, which is, of course, everybody is the most scared about that. There's a software environment for testing that. Most of our testing in the flight software team was done in Wistus, which is a software simulation environment where all the hardware is simulated by software. Then some of the hardware is added in the MSTB test bed. Of course, makes it more expensive. There are fewer of those test beds around. There's more competition. Basically, those test beds are used 24 hours a day, and you really have to fight hard to get a slot. And typically, when you get a slot, it's like at 4 a.m. in the morning for an hour. And then there's ATLO, where all the hardware and software are put together, and you do the final set of tests that you can do. Then there's also testing that's done for the flight dynamics, like the guidance and navigation control. Lots of different test beds of different fidelity. And so these things are being checked out very thoroughly, and typically it takes years, and simulation is done around the clock, 24 hours a day on big clusters for months on end, meaning that the rest of JPL basically has no access to all the clusters for all this time because you have less priority than a mission, clearly. And then ultimately, you hope that all of this combines and secures the success on Mars itself. So what about the software? So a lot of this is focused on the hardware, and actually most of the excellence in a place like JPL and other NASA centers has to do with accounting for hardware failure. What if this radio fails, or what if that wheel breaks off, or this axle, or this engine breaks? There's lots of stuff you can do with full protection systems to make sure that you have a redundant component in the system, and you can switch over at the right moment. But the software, so what about the software? It's about 3.8 million lines of software in the launch version of the code. Of course, we continue to update that code. We can uplink new versions of the software, and that has been done already a couple of times. The last time it was done was actually shortly before landing, where the final parameter settings and the final versions of the code were being uplinked. Typically, people get very, very nervous the closer you get to a critical event. If you change anything at all, even if you clearly have evidence that it is a mistake in the current version of the software, there are lots of hurdles to overcome before you are allowed to fix a bug. So if you, 3.8 million lines of code, if you turn that into text, it's about 60,000 pages of text. That's about an Encyclopedia Britannica that has to be written. 120 parallel threads of execution in this rover. So if you think, well, race conditions or deadlocks are not an issue, you're dead wrong, right? That is a major, major concern. It's written under the VxWorks operating system, adapted, so we have some customization. We get access to the source code for VxWorks for these, and we have a collaboration with Wind River, when it was still Wind River, to make sure that it fits our needs and our requirements. There are 2 CPUs, and then you can think, well, great, you can do some parallel processing, but no. The second CPU is a hardware redundant pair, like it's a standby in case the first CPU breaks or there's something off with the prime CPU, then you switch over to the secondary. So basically that thing is always idle until the hardware for the other pair, the other CPU breaks. We have used it once, so there's one phase in the entire mission that is the single most critical phase, and you just saw it, which is the landing. So for a long time, first we debated a lot about, can we use the second CPU during the landing to make things more reliable? And at some point we decided that it makes it more complex, much harder to test, and it's better just to fly on a single CPU and leave the other one off, completely off. At some point, about a year before landing, that still became a little uncomfortable, like, aren't we exposing ourselves to criticism? If the one CPU reboots in the middle of the landing, of course you're dead, you're going to crash. You will make it to the surface, but not in the way that was intended. So at the last point, about a year before landing, a small group of people got together and decided to write a separate thread of software with absolute the minimum functionality that could take over from the main CPU if it failed during the landing. That is incredibly complex if you think about it. Like, basically, the second CPU can wake up all of a sudden and say, now it's your turn, you take over. Like, I crashed, you take over. There's not enough time to reboot for the primary CPU. So it says, take over. Then you look around, you look at your sensors and say, where am I and what am I supposed to do next? As you're barreling down to the ground, right? So it's not a simple thing. But there was a software package there, was called Last Chance, and some called it No Chance, but actually, very luckily, that was not used, right? We never needed it because the main CPU did not reboot during the landing. 5 years of development time with about 40 software engineers. 40 actually is a puny number compared to the total number of people that worked on this mission. It's about 2,000 people that worked on this mission, conservatively counted. 40 people working on the software. Most people in the mission, in the project, ignored that completely. It was just a few $1 million. Who cares? Of course, they do a perfect job, and they just make sure that when the hardware fails in some bizarre way, or we encounter some unknown situation, that they will get us out. And if you have trouble getting the hardware to work, the software can fix it, right? They can work around it, etc. So there's a lot of pressure on this relatively small team. These are really, really good people, right? They have done this before. They've flown these missions. They really know their stuff. So if you work that out, 3.8 million lines, 40 people over 5 years, comes out to about 10 lines of code per hour, fully tested, not just typing in the code, but actually making sure that it is right. One customer, one use. So this is the sort of the difference with, say, Microsoft. You have a few million testers sitting around, unpaid testers who can get the bugs out of your code. Here, there's no such option. One single use, it has to work the first time. Very difficult to test because you don't have access to that environment where you really would like to test, say, the landing sequence. So how do you make sure that you get that right? Now, you don't have a number of options. Like, this is one of the options that you don't have. So you have to do something different. So I can tell you some of the things that we did to increase our chances of succeeding, to make sure that this software on this rover, even though it was about 6 times more code than had flown on the last mission, actually it was more software. All of the software is written in C for this mission on this spacecraft. It was more software than all previous missions to Mars combined, all of them, like all of the ones that successfully landed and the ones that did not. So 2 of them failed that we were responsible for, and 7 others succeeded. If you add up all that code, there's more code here. So 3.8 million lines has never been done. So now, if you're all familiar with the hazards and the obstacles in writing code and getting it right, how you test it, how you make sure that it works. Once you cross the line from a few 100,000 lines to a few million lines, you really cross a magical limit where certain things no longer work. For instance, peer code review, the way we would like to do it, like lock a few really good software developers in a room and give them a few hundred lines of code to look at, not going to work, right? 3.8 million lines is not going to work. You cannot do that. Still, we want to make this succeed. Like we want this software to be really robust. So I'll list 6 things here that we did that we had not done on previous missions. And we were very careful not to talk much about it, not to publish anything about it until after the landing, because basically I wouldn't have had this story if the landing would have failed, whether or not it is related to what we did. So first thing we did is we introduced a new coding standard. There are lots of coding standards. You've seen lots of them, and you've ignored lots of them in your life, and so have we. So we decided, well, all these coding standards are there. Basically, the way things worked at JPL before we started doing this was that every mission and every project that started off by defining a coding standard. They were all different, and they all had rules that were just related to cosmetics, like where do you put your comments, where do you put your curly braces, basically regulating white space. That's pointless, right? If you don't like how the software is formatted, run it through indent and define an indentation style that you like, where you want the curly braces, whether you want a space before a semicolon or not. Some people like that. Whether you want a space, etc. So you can do that. That does not correlate with risk. So we decided, well, first of all, we observed, okay, there are all these coding standards. There are hundreds and hundreds of rules in them. If you're lucky, the developer will look at the document and maybe flip through it and say, ooh, that's a lot of rules. But they basically won't follow the rules. I've actually done this experiment where I've looked at lots of software, flight software, for missions that we wrote, where we wrote the software, and where other companies like Boeing or Lockheed or Ball Aerospace wrote the code, ask for their coding standard, and you just pick a few rules and you check, does the code actually following the coding standard? No. And in many cases, it is very simple, right? Most coding standards have this rule. Every switch case must have a default clause. Grep -C switch, grep -C default. If the two numbers are wildly off, then there's a problem, right? And that's always the case. So even when you can check, people never check, and there are all these rules that are not related to risk. So we decided, first observation was, suppose you could pick 10 rules only, that are really related to risk, and if you say, if I can only get the developers to follow 10 rules, they will remember the 10 rules, which 10 would you pick? So we actually interviewed a lot of people, asked a lot of people, like, which 10 rules would you pick? And that led to the power of 10 coding rules. That formed the basis of a new standard that we introduced at JPL, which is in layers. I'll show you that in a little bit, where every rule is related to a mishap or an accident or a loss of a mission that happened to us in the past. So if you break one of these rules, we can say, if you do that, you risk that particular thing happening. So that's a great motivator, right? That really helps. So very few rules, every single one, we can show a case where we lost a mission or something really bad happened when somebody broke that rule. That's one. And we're checking, right? So compliance checks, tool-based compliance checks. You don't get away with not reading the coding standard, because whenever we compile the code, we check whether you comply with each of these rules. Second is we provide training, and actually we've now advanced to the point where we do certification of software developers. You cannot touch flight code without having this certification. Here's a picture of the first class that got certified to write flight code. So we now have this process in the works. There's something that I'm not listing here because it's not politically correct, and of course nobody is recording this, so I can tell you about this. We also have training classes for senior managers at JPL, because most senior managers don't have a strong software background. So we give them a one-day training course. So these are the executive at JPL who do oversight of the missions, so that they know what they're providing oversight for, and that they don't make really stupid decisions, right? So that they know where the risk is in software development. So we did that. Then we have daily builds. Well, that's not a big surprise, except it is a first for this mission at JPL. Every night there's an integration build, and we use static source code analyzers as part of the build process. with penalties for breaking the build. So the penalties are the obvious ones, and lots of companies have penalties like this. If you break the build, you have to have a Britney Spears poster on your cubicle for the day. And so people learn pretty quickly that they really don't want to be responsible for breaking the build. And at JPL, in this group, we used lolcat posters, and we just make it as unpleasant as possible to be responsible for breaking the build. We run static source code analyzers. Every time you compile the code for an integration build, we also run about 5 different static source code analyzers. Why 5? Because they all have different strengths. So each one of them, there's surprisingly little overlap between the warnings and the reports that come out of these analyzers. So we evaluated everything that was available commercially and academically, and we picked the top performers on flight code. And so we have Coverity, Code Sonar, Clockwork, SEML, and Uno. Uno sort of got a free pass in this because I wrote Uno, and of course we're going to use it, no matter how well or poorly it performs. So we run all of those on every build. Output goes to the developers. They have to deal with these warnings, every single one of the warnings. They're treated exactly like peer comments in a peer code review. So I'll say a little bit more about that shortly. We have a tool-based code review process. Based on this observation, if you have 3.8 million lines of code, you really can't afford to look at a few hundred lines at a time because that'll tie up your team for forever after, long past this mission is going to be over. So you have to do something different. So we have a strongly tool-based process that I'll show you a little bit more about in a little bit. Unit testing, for the first time we required 100% code coverage, which is, as you know, probably surprisingly hard because you also have to deal with defensive coding practices, like basically the case where you say this can't happen. So there's code to handle this here, but it can't happen. You have to be able to test that it does what you intended to do if the thing that can't happen happens. Daily integration testing every night. Full integration test suite happens. Anybody breaks that is also responsible. And then we did logic verification of critical subsystems. So this is the part that you probably expect me to bring up because we really did that quite a bit on this mission. All the key subsystems where we were worried about race conditions, deadlocks, possibility for data corruption or data loss, we did a full-blown logic verification of that subsystem. Led to a complete redesign of some of these subsystems. So some of the subsystems, like the data management subsystem, was completely scrapped and replaced based on our analysis with the model checking. So we found so many issues there that it was decided to just redesign that entire subsystem. So I'll talk about a few of these. Many of them will be obvious, what is meant by these, but maybe not all of them. So the coding standard, we based this on the power of 10 rules. Went into a JPL institutional coding standard that is now required for all missions and all projects at JPL that write software, which is quite a few of them. Now, not easy to get everybody to agree to a coding standard, right? So to a single coding standard, overruling all others that they may have used in the past. But we had a very strong case. Basically, the case is you're not following your own coding standard anyway. So this one we can check. So there are different levels of compliance in this coding standard, similar to the CMMI, like this quality control system from CMU. So there are 4 levels of compliance. There are about 32 rules at the first 4 levels of compliance. Missions with mission-critical software, like MSL, are expected to comply with level of compliance 4. Now, if you have test software or non-critical software that is not on board the spacecraft, you can get away with lower levels of compliance, but you cannot get away with a level of compliance less than 1. Now, what is level of compliance 1? So, of course, that is the one thing that we say everybody has to follow that rule, no matter what. No excuse. That's absolutely no excuse. Can't say it's non-critical. Can't say, we only use it once. Oh, we've run it for 10,000 hours in the test bed. It has never failed. No. So there are 2 rules at level of compliance 1. Rule 1, which turned out to be surprisingly difficult to get people to comply with, but it's a no-brainer, is you have to compile your code without warnings. 0 warnings. 3.8 million lines, 0 warnings. Not just that, with all warnings turned on and with pedantic turned on, 0 warnings. We did that for MSL. It took 3 years, but we got to that point. And at that point, we could turn the compiler, we could map warnings to errors and saying if there's any warning, no matter if otherwise it's just a warning that you would normally ignore, it breaks the build. So that works really well, right? That works really well. So we're at 0 warnings. It also says 0 warnings from static analyzers, which is harder. It's a lot harder because there can be false positives from static analyzers. They can think, well, there might be something fishy about this code, but actually it's not a bug. So we say, well, even in that case, if it confuses the static analyzer, you should fix it. You should rewrite the code that is obvious, even to that tool. MSL, we didn't quite get to that point. There are still a number of these warnings that were left in the system because there wasn't enough time. The one mission after this is called SMAP, which is an Earth orbiter. They have reached that point as well now. So there's completely 0 warnings from all static analyzers and 0 warnings from the compiler in pedantic mode. Rule 1 is use a static analyzer and have 0 warnings from static analyzers and from the compiler in pedantic mode. Everybody has to comply with that rule, and people have a hard time dealing with that. So there are 32 rules, and the chapters are sort of evidence. Now, if we give certification courses, we talk about these rules and why they're there and what may happen if you don't follow those rules. There are 2 more levels of compliance, and they're intended for safety critical code, meaning if the code is human rated, like it's a human being whose life may depend on you getting the code right, then there are 2 extra levels. And they are based on the MISRA standard, which is a standard, or it's really guidelines used in the automotive industry for control software for your engine control software. Actually, I was fortunate enough to be on this team that investigated possibility for unintended acceleration in Toyotas that you remember from about 2 years ago. And so we got the chance at looking at real engine control software from Toyotas, which nominally complied with that, and that's all I will say about that. Now, code review. Experience of anybody who has actually ever looked at this is that if you impose a standard, everybody will say, yeah, and they will ignore it, right? They will not follow the standard unless you check. If you don't check, you might as well not have the rule. It's like, teaching a pig to sing. It doesn't work, and it annoys the pig. It's just completely pointless. So we have a tool-based code review process that is integrated with compliance checking for the coding standard. So this is the tool that I wrote. It's called Scrub. It's a code review tool, and basically every module. So this is actually a snapshot of one of the real code review. The reason I can put it up here is in that module that we decided to redesign and throw away all the code. So this is flight code, but it's not flying, right? And it will never fly. So, but we did lots of reviews of that. So basically, this interface is very, very simple. Right? It's really, the GUI is extremely simple, but very effective too. So peer code reviewers get assigned a module to review the files, bring up the file, each file in turn that they have to look at, walk through the code, they have to read the design documents, click on a line number, enter a comment, and it comes into the peer code review box. The module owner, which is the guy who wrote the software or who's now responsible for it, often it is heritage software that came from a different mission, and there's a new victim now responsible for it who was disgusted with the code to begin with and doesn't want to change anything because he doesn't really understand how it works. So all these comments are collected. So here's a comment from Steve Skandor. Importance is associated with the comment as high, medium, or low. Default is medium. Here's a high priority comment on this particular file, that line number, which is shown here. There's also a little tag here. If you click on it, you see the comment on that line. It says, does this require a lock? So there's a lock here and an unlock, and he says, do you need that lock? And there's a response from the module owner. It says, I disagree with removing that lock. It's actually needed for this and this reason. And then there's a final resolution of this. So code reviews are done offline. At night, in the evening, during work hours, whenever the peer reviewer has the time to really concentrate on doing the review. Then at the end of the code review, so there's typically 2 or 3 peer code reviewers assigned. They go through the code, they annotate lines with comments, questions, queries, observations. Then there is a single meeting that is typically quite short. It's 1 hour, 1.5 hour max for each of these modules, where we go through the comments and the responses of the module owner. The module owner must respond to every comment entered. If he does not respond, the implicit response that the system, that the tool will assume is, I agree with your comment, I'll fix it. That works really well, right? That works really well. So in the initial few code reviews, a lot of people said, I'll just ignore that, I won't respond, and then they get an assignment, fix the code, because you have an implicit agree on that code. So here's the response from the module owner, say, I disagree, I don't think we should fix it. And then in the code review meeting, we only talk about disagreements. We don't talk about anything where there is an explicit agree of the module owner saying, yes, you're right, I'll fix it. That was wrong, or that could be clarified. Don't have to talk about it. We only talk about disagreements, and it's a very small subset of all the comments that go into this peer review. So here, Ben Sicci is the coggy, the cognizant engineer for the mission who led the code reviews. He says, I agree with the response, no action required. It could also be that he would have chosen, I disagree with the disagree, I overrule you, you have to fix the code anyway. And there are quite a few of those cases. You can sort by importance, by name, by things pending answers. So here you can see 117 of the comments had an agree, an explicit or an implicit agree. Only 10% of them had a disagree. Only those had to be talked about. There were a few that were marked like, I don't understand the observation, let's talk about it at the code review. And then there were 4 that were not responded to, so it's an implicit agree. So now you see all these boxes here, right, that have these nice bright colors. That's very deliberate. So there's one box here that says, we're going to compile your code with GCC. That's not the flight compiler, right? It's embedded C code going to basically a PowerPC equivalent. It's a RAD 750 running at about 200 megahertz in this rover. So we're going to compile with GCC because part of rule 1 that I didn't mention is you have to be compliant with the language. You can't go outside the language. You can't rely on any feature in the compiler that you happen to be using for the PowerPC because that's not allowed. It has to be portable. You have to be able to compile it on our simulation platform, etc. So we compile it with GCC. So pragmas are not allowed. There are no pragmas in this code. It's green because there are no warnings, and there are required to be no warnings. Now, if the box here, so GCC strict is pedantic, and there are a couple of others. There's Coverity, CodeSonar, UNO, and MSL. And they're not green. They're supposed to be green at the moment of the code review. For this module, they were not green. They're orange. That means there are between 1 and 10 warnings from this static analyzer. So here, Coverity is a static analyzer. It generated between 1 and 10 warnings. There should be none, right? The code should be rewritten to avoid all these warnings. CodeSonar had between 1 and 10, and UNO had between 1 and 10. All of these buttons have to become green before the module is accepted to be flown. Then MSL had its own coding rules in addition to the coding standard. So every project can add their own rules. So one of the rules that was checked here in the MSL coding guidelines was every if-then-else chain. If you have an if-then-else-if chain, then the last clause in that must be an else. Because if you don't do that, you have something similar to a missing default clause in a switch statement. So the last else is an uncovered case, right? If you forget the last else in an if-then-else-if, then you may miss a case. So that's not allowed, and we check for that here. If the button is red, you have more than 10 warnings in that case. So that's now getting extra attention. So what this tool did, this scrub tool did, was it treated tools, static analysis tools, and rule checkers as peers. They did the code review. Every night, on every build, they did the code review. These analyzers went through 3.8 million lines of code and flagged every violation of a rule that we had. And then it did the color coding. So the color coding has a psychological effect because in 1 second after bringing up this display for the module, you can walk through all the 120 different modules. You look at the color coding, you see immediately what the relative quality of that module is. So at some point, it became a matter of pride for the software developers to get all buttons to go green. And they worked really hard on that. Every night also, we compiled a list of the worst offenders like the highest number of warnings, and that became, and we melted out, like the 3 modules with the largest number of say covariety warnings. That became known as the wall of shame. Now everybody did everything in their power to not be in the top 3 of the wall of shame. So over time, that has exactly the effect that you want, right? All the warnings go down. Okay, we did this every night, and so based on the nightly build of 3.8 million lines of C code, there's a make that runs. In effect, it's much more complicated than a make, but you know, by first approximation, it's just a make. There's a build log. We extract all the compiler calls. It's about 3,000 C files, .c files that get compiled. And then we do defect detection with static analyzers and coding rule compliance. So defect detection, we use all these tools. Coding rule compliance, we check against the power of 10 rules. We check against the JPL standard. And we check against the MSL volunteered rules, like we're also going to comply and insist on compliance with these rules of our own. So there's these different levels of compliance. Then we take the output of all those tools and we consider them as peer reports. They're formatted to look exactly like what a peer would comment on the code. So it looked like these tools went through, clicked on the line number, entered the comment, and that was that. There's some triaging depending on, you know, how close are we getting to deadlines and how much time, how much pressure do we want to put on developers. So we sort of discard things of low importance and let the rest through, and it goes into the scrub database. And so then it colors these buttons, and then the next morning, the module owner comes in, looks at the buttons, and tries to get them to go green. Now, if we upgrade one of these analyzers, we get a new version with better checking, then, you know, a button that might have been green before turns orange again, and then people are not happy, and they have to work again. Now, if too many of the buttons went green, since I sort of worked behind the scenes to get this mechanism to work correctly every day, if I saw too many buttons go green, I would turn this knob here and I'll let more things go through so that people don't get a false sense of security that things are just, you know, perfect. How long did that take? Well, that takes a long time, right? So the global analysis overnight, it started pushing against the limits of what an overnight run is. It took about 15 hours. Most of that time actually was taken by one tool, CodeSonar. It was about 12 hours. There's a very thorough analysis. Now, next morning, module developer comes in, fixes warnings, and wants to make sure before the next day that he actually fixed the problems and not pushed them around. So he can do a shorter check of his module alone, ignoring all the rest. Now, that's not as precise, but it gives a first indication of whether he actually fixed the warnings or not. That takes about 10 minutes per module. So did it work? Well, this is statistics that we got at some point after about 3 years of running this process. So at that point, we had reviewed about 500,000 lines of code in 130 models. Actually, we went down from an initial 164 modules down to 120 in an aggressive effort to simplify the code. 20,000 reports, 16,000 actions. So here, the peer comments and tool comments. You see that the percentage of warnings and reports that led to an action, like a change in the code, which is a nice indication of the truthfulness of the report. So it's about 80%, both for peers, slightly higher for peer reports than for tool reports, but roughly 80% of all the reports led to a change in the code to suppress that warning or to avoid it or to make it not come up again. Number of disagrees for peers, about 30% of peer comments were disagreed with, but the majority, 70%, were agreed with. And for tools, it was fewer, because basically people probably had the feeling there's no point arguing with the tool. It's not going to change its mind, right? It's going to insist. And then here's the percentage of overrides. So for peer disagrees, 68% or so of those were overridden, saying, fix it anyway. Like, you disagree with the warning or the report, fix it anyway. We don't want to see that warning. And lower for tools. And then, you know, so this worked remarkably well. So overall, over the entire period, we had about 10,000 peer comments on the code and about 30,000 tool reports. and the vast majority of those were changed in the flight code before we launched. So the question is, did it make a difference? Now, it's just, so far, it's just feel good, like we're trying to do the right thing. Does it actually work? So here's statistics. I tried to track. This is from 2008 when we started in January with this process, this code review process, until 2010, October 2010, when we reached 0 on compiler warnings in strict and in standard mode. So you see that bar tracks the number of warnings from the compiler, compiling the flight code. And then I'm also tracking coverity warnings. Now you see they're trending down. So you could say, well, that always happens. Of course, people are working on this. It's really, really important. You don't want to hit front page of the New York Times, and you don't want to be identified as the one person whose code, made you lose $2.3 billion. So, of course, this always happens. Now, we happen to have a lot of data on previous missions, since we flew the previous missions. The one that was immediately before this was the MER rovers. And we did not follow this process. This was before I joined JPL and before we introduced this process. So I tracked it for the MER code. And so here's from 2002 until 2006, so 4-year period also, looking at compiler warnings in plain mode, there's the blue line, in strict mode, pedantic mode, and you see it's not trending down. If nobody's watching, it's not trending down. The code doesn't compile without warnings to begin with. Nobody's paying attention. Number of warnings goes up as the pressure towards launch builds. Now, surprisingly, the number of coverity warnings did sort of slowly trend down, even though we never ran the coverity analyzer on that code. That was before this really was available. But you see the differences. So 6.6 compiler warnings per 1,000 lines of code, and here none. 9.6 per 1,000 lines in strict mode, and here none. 1.4 static analyzer warnings per 1,000, and here 0.7, so half. But the most important is the trend of this. So this process tried to impact the way the software was written, and we have some data to show that it did. So now there's one part that I did not talk about, which is, to me, the best part, like the logic verification of critical subsystems. As you may know, there are ITAR rules related to flight software. It's considered missile technology. So I cannot show you anything that really is part of this mission, because basically I'd be out of a job tomorrow if I did that. But I can show you the process. I can show you how it works on something that nobody cares about. Let's verify a lock-free 5.0Q. Like, who cares, right? But so, and you may have written that code, and you've tested it, and you've made sure that it works, and maybe in lots of hours of usage, you've never seen it fail, but you may still have in the back of your mind, there might be at some point different CPU speeds, different usage patterns. It might fail. How do you rule that out? So in this case, for this mission, we absolutely had to rule out these kinds of race conditions and bizarre multi-threaded scenarios. So it's a lock-free queue with multiple users. Now, to keep it simple, I'm going to assume one reader and one writer. So this is a standard producer-consumer problem without locks. And it's sort of, it's a macho thing. Whether or not you think you can get away with it, it's kind of a macho thing to say, I'm going to write it without locks, right? Because nobody likes semaphores and locks. It'll kill your performance. And so in a rover running at 200 megahertz, you don't have a lot of margin, right? So the first indication of every developer who thinks he's really good, and everybody does think that, even if you're not, is to say, I can do that without locks. And then 90% of the cases, you're wrong, because you're not thinking of a particular scenario. So here's the problem. There's a concurrent update problem. And the only problem is switching between these two states. So here the queue is empty. The head and the tail point to null, and the queue is empty. Here's one element in the queue, and the head and tail point to the same element. And here there are two or more, head and tail point to different elements. The only transitions that are difficult with multi-threaded concurrent updates is to transition from here to here. And so it's when the reader, when the queue has one item here, and the reader takes it away, and we go to that state, and both head and tail have to be updated. That's a problem, because now you can only do one at a time without locks, and you can get out of sync. And so the writer can come in at just the wrong moment. The same with the writer. When the queue is empty, and we want to transition to here, both head and tail pointers have to be updated. So how do you get that right? So one algorithm doesn't take too long to come up with this particular method, although I haven't seen any papers published on it, but no doubt it exists somewhere where I wasn't looking, is to say, just make sure the queue is never empty. So make sure that that state doesn't exist by always having something in the queue. So you always must have an element in the queue. If it's not a valid element of the queue, you have to mark it as free, like it's part of the free list. It's always there. So then every update only updates one pointer, and that's easy to do in a concurrent update scenario. So when you remove this element, say this is a real element in the queue, when you remove it, you mark it free. When the reader comes in, looks at the element, says it's free, tries to follow the next pointer, and if there's no non-free element, then it says the queue is empty. If there is another element, say this one is marked free and that one is not marked free, the reader comes in, the head pointer is here, it says free, moves the head pointer, points here, and now it marks this one free and removes it. Removes the contents, right? Not the slot. So the question is, how do you make sure that that works? So you can reason through it and think, yeah, that feels right. That has to work. You can implement it, test it, it all seems to work, but how do you prove it, right? So we needed to prove for these critical subsystems that they absolutely worked, or more likely that we wanted to find the sneak paths where it would not work. So here's the code, not too exciting. You can write that code in your sleep. So, but here's something, and you can get it right or wrong in your sleep. One case is more likely than the other, but okay, there's your code. Correctness, how do you prove something? How do you really prove it? Which cases do you have to test or prove? There's this theorem from Pierre Wolper. It's actually a very useful theorem to know about. Not too many people seem to know it, but it was published in Popple in 1986. Pierre Wolper, of course, worked at Bell Labs as one of our colleagues at the time. Published in Popple, and he came up with this theorem that says if you want to prove that, say, a bounded buffer or a producer-consumer problem, that it is correct, that you cannot lose messages, you cannot duplicate messages, and you cannot reorder them, all you have to prove is that it works for 3 different items. So if you send an integer, say you have a cell, and you send an integer number through the queue, how many of these integer numbers do you have to test? And his answer is 3. Exactly 3, no less than 3, and no more than 3. And so you color them, you say red, white, and blue, and the data stream you have to send is an arbitrary number of white messages, followed by exactly 1 red message, followed by an arbitrary number of white messages, followed by exactly 1 blue message, and then a white message. At the receiver, if you get this thing is in a really bad place. If you get a sequence of messages that matches that regular expression, it is correct. And if you can prove that it must match that regular expression, you have a proof of correctness. And so if you can have reordering, red and blue could be reordered, and you have to prove that that is impossible. If you can have loss, one of the 2, red or blue, could be lost, right? And you have to prove that the first message you get cannot be a blue. It has to be a red, and it has to be followed by a blue. And if you can duplicate it, you can get 2 blues or 2 reds, etc. So it covers all these cases. So that's the data stream. You write a tester, and again, so you can write this tester. Here are 2 assertions that say when you get the red, you can't have gotten a red before. You get a blue, you must have gotten the red before, and you can't have gotten a blue before, etc. And then you can run this in a test ad infinitum on as many machines as you want, and you're still not sure. So we want to prove it. To prove it, here's the one nasty part. You have to write a test harness. Now you have to write a test harness, and I deliberately use this term test harness because you have to do that anyway, right? You have your tester, you have to set it up and say, run this test, and run it 1,000,000 times. Now I only want to run it once, and I want to prove it. This is what the test harness looks like for the model checker. And now your eyes glaze over, and you say, really? But it's only 16 lines, right? It's not that bad, and some of it is just saying, this is the file, the .c file, where my code is. And these are the get and put procedures that I'm particularly interested in, and I want to instrument them. So there are these I calls, qput and qget are instrumented calls. Here's my sample reader and sample writer. That's the tester. So this is not really like rocket science to think of that. It's just a particular format to specify this is what I want to check. And then I have an explicit heap allocator that the model checker would like to get, and you import stuff and you track stuff. So this is not magic. You can learn how to do that. If you do that, this is what you get in return. Use a model extractor, freely available. Run the model checker. It invokes it. So I just extract from the .c file. Note, I'm not writing a model. I'm giving it a C file. I say run the verification, runs the verification. Happens to take only 3.6 seconds, but this proves that it cannot fail. There are no race conditions, no deadlocks, no life locks, no data corruption, no duplication errors, etc. So this is as close to good as you can get. And we did basically this procedure on the C code. We also did handwritten models. So the most complex analysis that we did was a larger subsystem where we spent about 6 months hand-building models that we could then verify with the model checker, because it really mattered in that case that we got things right, and we found lots and lots of problems. So this case where it says errors found 0 is highly unusual, and if this is the first result you get, you should be very suspicious about what you were doing, right? Because almost certainly you initially make mistakes. So let me stop with this image, which to me is probably the most remarkable picture ever taken in the history of mankind. Okay, with that build-up, right? What is the picture? You can't really see it with the contrast here, but basically this shows the crater on Mars, where we landed, and there are wheel tracks starting in the middle of this valley here. There's nothing there, right? There's in the middle of the valley, there are wheel tracks starting, and somebody drives away. Where did he come from? He came from the sky, right? Came from the sky, from a different planet, and drove away. Now, if this is not like an accomplishment to be proud of, a technological engineering accomplishment, if you can do this, right, you should be able to do just about anything. That's it.
So one source of error in your logic verification is the test harness, building the test harness, of course. Did you ever consider to use high-order logic verification, whole-based verification, where this mapping is done by tools? So this removes that kind of things.
We're very keenly interested in that. So we have people in our group. There's the Lab for Reliable Software. That have a lot of experience with theory-improving systems. I have a PhD student at Caltech. I gave him the assignment to do that. And I had to stop him after 2 months because he was falling too far behind on his PhD topic. Very, very difficult to do. So there are lots of examples that you can look at where even algorithms of the complexity that I just showed you, the 5.0, log-free 5.0Q, on average, takes you about 3 months to do something like that, so it has to be really, really important. And of course, in our case, it was. But the complexity of the subsystems that we had to analyze was larger, so we ended up using this.
So pretty recently, NICTA in Australia, the National ICT of Australia, reported that they had a full verification of a full L4 microkernel.
Erwin Klein did that project. Yes, very impressive. Yep, a lot of manpower behind it, but yes. Mm-hmm. Yeah.
So I'm curious why you're still writing code in C, and wonder whether you considered using a different programming language that might be easier to analyze.
I didn't expect that question here, but so I have an easy way out. When I write code, I write C. That's not the answer, right? So I prefer C, and a lot of my colleagues prefer it. It's a simpler language. It's better, the devil that you know, etc. But I can give a very pragmatic answer. I don't care what the software is written in. I just want to know what it is. 96% of the flight code at JPL is written in C. I could try to fight a battle saying it has to be Spark Ada, it has to be Scala, it has to be whatever, you name it, right? I would lose that battle, right? I would lose all my influence elsewhere if I tried to do that. There's a long tradition. Well, actually, it's not that long. So it started 1997 with the Pathfinder mission to Mars. Glenn Reeves did that mission, and was written in C. And ever since then, that heritage has continued. So it's 96% of the flight code is C. The only mission where they used Ada was Cassini, which is still in orbit. It's active around Saturn. But basically, the problem is we're flying C code, and we have to do something about that. And I could wave my hands and say it should be something different, but I won't get anywhere. People have tried, and ultimately it has to change, right? But yes. So this is about. So sometimes I've given the analogy as well. There's somebody with a locked door and nobody knows how to get in, and there are all these people selling snake oil. Say, I know, I have the key, and then the key doesn't fit. And then so the typical snake oil salesman will say, I know how to open the door, I have a key, and walk up to the door and say, now first change the lock, right? And then my key will fit. And that's this, like, change the language, and it doesn't work. So I have to accept that's the problem, and we have to do something.
So first of all, thank you very much for a wonderful talk. It's rare to hear such direct experience with a successful mission. And precisely because it is such a rare talk, I have the following question, which is that you talked a lot about removing warnings, but I still don't have a good sense of how that impacted the quality of the software. I understand it's difficult to really measure that. So I was hoping you can comment on that. And another question is, I was a little bit surprised to see how much focus there was on process. Surprised not because that's not what we would expect should be used for everyday software, but in this context, at least it sounds from your talk like the process was the secret. We fixed the process and now the mission worked. I mean, if you can comment on that as well, sure. I'd appreciate it.
I forgot the first part of your question.
The removal of warnings, how
right,
does that impact quality?
Right, so absolutely right. So we can only measure indirectly, right? One big milestone and point of truth is the landing, and so far the mission. So far, there have been no significant software anomalies. And I add the adjective significant, even though I could leave it out, right? There have been no software anomalies in this mission so far. There have been hardware issues, and there have been issues with people using the wrong parameter settings in the code, which I don't consider to be a software coding issue. But this has never happened before. So typically up to this point, there have been major issues where we lose mission time to figure out what's going wrong and how it should be fixed. So that's one indication. Now, it's also not, correlation is not causation, and so we don't know. But and there have been fewer problems in the software reported in the various test beds. So I showed you that the various, like Atlo is the most thorough test environment with all the hardware that we have. But very few software issues have come out of that, which is very unusual. So there are a lot of things that have gone unusually good, even though this is a far more complex mission than any of the ones that have flown before it. So even though we can't measure this directly, the only real measure is what actually happens on the surface of Mars and the way there. And all the indications are that so far it's a remarkably clean mission. Even somebody remarked that watching all the data from the landing sequence, no single simulation that they did, no single test that they had done of this entire sequence has gone as perfectly as the real one on Mars. And that's precisely how you want it, right? So how do you measure that? If you know a way of measuring more directly, I'd love to know what that is, but we only have circumstantial evidence. And the second part?
Process versus logic.
Yes. Well, I did talk a lot about process. It's tools, using the right tools, and using tools, mature tools that are available to you. In our case, static analyzers. I don't know if you want to consider that process or just proper work environment. Not allowing warnings. I think that's just a matter of workmanship, right? It's just, not cutting corners. Process, I would not have described it that way, but I guess it does make that impression. That's not deliberate. So no managers have been involved in what I talked about, right? This is all engineering decisions. Let's do it this way. This coding standard. So we got a lot of input from Dennis Ritchie and Brian Kernan, Ken Thompson, and people around that on the coding standard. We asked a lot of people, what do you think should be the rules in this standard? How should we check these rules? So these are engineering decisions of knowledgeable, competent people, where typically process is typically associated with people who are not very knowledgeable and think they know what they're doing.
Great, thank you very much.
So at some point you mentioned that you used, in one of your critical systems, you used spin to check a model of the implementation and not implementation itself.
Yes.
I'm curious to know whether, how was that model derived and whether there was some way of connecting it back to the implementation.
Yes, so it was derived first by looking at the design. So of course we look at the code and then ask lots of questions, what is it supposed to do? Build these models, so it's an abstraction of the design that you have a hope of verifying exhaustively. Lots of discussions with the module owner, the designer of that code, saying, is this what you meant? Simulations, lots of simulations showing, is this how it should behave? And then when finally you have everybody signing off like that captures the design, which is a process of several months. Then running the verification and finding the errors. And now the moment of truth, like, when you find a violation, we found lots of violations of key properties. Like, what are the properties, right? So what is it supposed to do? And formalizing that. And you get the violations, and then you walk through it and say, can the actual code do that too? And in some cases, the answer is no, and then you adjust your model because you made a mistake in the abstraction. You've forgotten some detail. That happens a lot initially. And at some point, the answer is yes, thank you, I'm going to fix it, right? Yes. So there's no easy road. It's just do the work. And